Hey guys, welcome back to AI for Teens. Today I'll be talking about training on MNIST dataset again, but the difference is I'll be talking about convolutional neural network. Last time we've talked about simple neural network, but now I'll be talking about the convolutional neural network, which is CNN. What is a convolutional neural network? CNN stands for convolutional neural network, as I mentioned. A CNN is smart. It looks at small parts of the image um, like ears, eyes, and fur, just like the smallest details. And it learns to detect important features using something called filters, which I'll be mentioning now. These filters slide over the image, looking for patterns, for example, edges, shapes, textures, and etc. Just for anything that's patterns. As the image passes through multiple layers of the CNN, the network builds up more complex understandings, like first detecting lines, then shapes, and maybe a cat's face. So, as we're learning, we, I can even take a human example. Once we're learning math, for example, we don't directly go to x 5x equals 25. Like maybe you guys can solve that. I can probably solve that. But like you first start off as a toddler with what 1 plus 1 is, and you keep on building on, and then you can get to what 5x equals 25 is, or more complicated math problems. Convolution is a mathematical operation used in signal processing, image processing, and deep learning, especially in convolutional neural networks like CNN, which stands for CNNs. It helps extract features like edges, textures, or patterns from data. So it's basically just a summary of what we just understood. Important properties in CNN. Number one is convolution. Core operations in the CNNs. Um, Convolution is the fundamental building block of convolutional neural network. It's in the name. Used to extract features from input data, like images. So it just gets all the details from the image. Involves a filter, which I have already mentioned. It's basically a kernel. It's a small matrix. Like for example, when we mention a 3 by 3 pixel or a 5 by 5, it's called a kernel or a filter. It's slid over the input image. Performs element-wise multiplication. So AI is all over math and numbers. So it already just has these fun names. At each position, the filter is multiplied with the overlapping portion of the image, and the results are summed to produce a single output value. It's kind of how it works. Like compared to the simple neural network, we notice that there's very less steps, but the CNN can also train faster, but it has all of these steps. It's just explaining what's happening. And it produces a feature map. The process generates a new matrix called a feature map or an activation map with highlights, certain patterns, edges or textures, as I mentioned on the first slide. Captures local patterns. So convolution focuses on small regions at a time, allowing the network to learn localized features like corners, lines, and textures. I also mentioned all of these on the first slide. It's just going more into detail. Okay, so this is part two. Now we're talking about pooling, which is subsampling, basically, it's what it's called in another way. It improves computational uh efficiency. So it's a very sounds very complicated, but if I break it down, it's going to be very easy for you to understand. Smaller feature maps means fewer computations and faster processing in deeper layers. So what it's trying to say is the more layers there are, it's still is faster in processing all of the data, like the input layer, output layer, hidden layer, and everything. It helps prevent overfitting. So, By reducing the number of parameters in spatial resolution, pooling introduces slight invariance and improves generalization. What this is trying to say is basically is reviewing all the data, so it's very easy or very much more accurate than like other smaller neural networks. Common types of pooling, max pooling, takes the minimum value of each patch of the feature map. Average pooling takes the average of all values in the patch. Again, math. Uses pooling window and stride. A typical pooling window is 2 by 2 with a stride of 2, meaning the window moves 2 steps at a time. So stride is basically steps. This effectively reduces the feature map size by half. So that's very cool. Maintains important features. Pooling retains the most important or dominant features like edges or corners, even if their exact position shifts slightly. So if point A is here and point A moves like even the tiniest bit that it's very hard to notice, it's AI, the CNN, is even going to notice that. And now we're in part 3, which is our last part of this. Layers. Convolutional layers. We've talked about this a lot, like plenty. It applies filters to the input to extract features like edges, textures, or patterns, as I mentioned, produces feature maps that highlight different aspects of the input, and has learnable parameters like weights and biases, as I mentioned in my videos. The activation layer applies a nonlinear function, usually the ReLU, which stands for rectified linear unit, to add non-linearity. So just activates it better and more accurate in less time. Helps the model learn complex patterns by breaking linearity. So similar thing. Pooling layer, which we have already mentioned. Subsampling reduces the spatial dimensions of feature maps. I've talked about that. Helps retain important features while reducing computation and overfitting. So it's just going like very important properties, which I've mentioned in these slides. Okay, the difference between CNN and simple neural network. CNN is more accurate when trained with fewer epochs. Um, Once you train it, let's say even you train it on 15 epochs, it can be more, let's say like 98.85 random to make it more accurate. But even if you train with the simple neural network in 50 epochs, it might be like 97. So it's much more quicker and more accurate. It's built for image data, which we literally use AI for now. It's specifically designed for 2D image inputs using local filters to capture patterns like edges, textures, and shapes. It's efficient use of high resolution inputs. So, a 256 by 256 RGB image would require over 196,000 input neurons in an MLP. CNNs can process this efficiently using small convolutional filters and pooling layers. So, as you can tell, this is a really, really big image, like 256 by 256. And over this much, you can train this on 15 epochs, and it's literally going to give you what you want, which I think is really crazy because this is such a big number, and CNN can literally just do it in no time. Local connectivity and receptive fields. CNNs only connect neurons to small regions to the input, which is called receptive fields. Preserving spatial structure and capturing localized features. So this is trying to say that the CNN is only connected to neurons in the small regions of the receptive fields, which is a spatial structure capturing local features. So the neurons are, let's break this down. The CNN only focuses on neurons to the smaller regions of the input when, and in those input, it's categorizing localized features, which is like the fur, the eyes, or the ears. Weight sharing, parameter efficiency. CNNs applied the same filter across the input image, allowing the network to detect the same feature in different locations, reducing memory and computation. So, this is just saying how you can save much memory, much more data when training with the CNN. And it's faster training and inference. Due to fewer parameters and efficient GPU optimized operations like matrix multiplications and convolutions, the CNNs train and runs much more faster. Why choose CNN? It is great for image data. It's designed to work best with images and visual patterns. It automatically detects features like edges, textures, shapes, and objects on their own. Fewer parameters. CNNs use shared filters, so they need fewer parameters to fully connected networks. So that means it's less memory that it's taking up, which is a good thing. Faster training, which I already mentioned. Um, as I already said, with fewer parameters and efficient computation, CNN trains faster. Less memory needed. I already mentioned this, it's part of the fewer parameters. Smaller models means less memory usage compared to traditional networks. Better accuracy. I already mentioned this on my last slide where it's even higher accurate than simple neural networks. And when it's trained on less epochs, it's still more accurate than simple neural networks trained on more epochs. Works well with large images. As you saw, the 256 by 256 images, it's very accurate still. Reduces overfitting. Because of local connections and shared weights, they generalize better. Built-in spatial awareness. CNNs preserve the spatial structure, position of pixels in images. So mm, it's very really good to use than simple neural networks. But if you're just starting off, then you can use simple neural networks. But CNN is much more efficient. Okay, now we're here at the code. I will be explaining this code. So these hashes, maybe you'd call them hashtags. I do too, but it's like in this talk hash. So these hashes right here, the AI completely ignores them. So if you add hashes, the AI does not even see them. When you're training, they don't see it. So it's just for your help. And um, all of these are defining the model. So when you give it, first of all, you always need equals. Like most of the time, I'm using these equal signs, which shows that you're giving it a label. You're giving each of these things a label. And I also mentioned it here. So the epochs are 50 in this case, so it's labeling everything. Okay, so the training loss. The accuracy was 97.72. I did train this on 50 epochs. As you can see, it starts off here when it's just testing model. Then it starts to become, okay, we're getting there. Okay, now I see it. Okay, it's bumpy and it's completely straight. That's crazy. The inference result, I created a load predict CNN.py. Um, file this time. Last time I created a load and predict.py file. Then I loaded the train model, then I'd input an image from the test data. I used the same one as last time. And as you can see, it predicted the digit 5. And as I mentioned in my last video, maybe the training data gave it this 5, but in the testing data, it got a weird, or not weird, but just different handwriting 5. And that's it for today's video. I hope you guys understood the difference between CNN and a simple neural network. I will see you guys next week. Bye, guys.